Hello, and welcome to the Ozeki Journal Club. I'm Carlos.
And I'm Perry.
Hello, Perry. How are you?
Not bad. Yourself?
Pretty good. Pretty good. Are you excited for the elections?
Pretty excited.
Me
I
too.
want to see what's going to happen.
Yeah. You didn't place any bets in the end, eh?
No, I didn't place any bets.
Me neither.
It's too risky. It's too anything. It's like, I don't know. You can't make a logical, you can't make a logical guess, but.
No, but it's a feeling, right? You bet on sports?
Sure, but there's like the variables are much more limited.
You think?
Yeah, I think so.
How come these poll people create these like super confident predictions, you know?
Well, they did it last year also.
Yeah, I guess. I suppose. Oh, yeah.
That doesn't mean anything. I guess it could be an outlier or whatever. I don't know.
Well, I find it crazy that like people spend a crazy amount of time trying to predict this, you know?
Just wait.
And like the stock market is up already because they're assuming that Biden's going to win and that he's going to push through like a huge stimulus plan.
Oh, really?
Yeah.
I didn't know that. Wow.
You got to check your Wall Street Journal.
Nice. But if Trump wins, doesn't the economy go up? Like, I don't know.
No. Well, I don't know. I think Wall Street likes to have like these stimulus packages. But I don't know. I mean, I guess they would care about inflation. So I'm not sure like what the time scale is. But every time like there would be an article that says Trump delays stimulus package.
Yeah, it would crash.
Boom, S&P goes down.
Huh.
I don't know.
Okay.
I'm happy with my gold stock, so everybody gets some gold.
There you go.
So today I thought we could spice things up a bit and try a non-blockchain paper. Just because why not, I suppose. And Perry agreed to it, so I think
after a rebranding of the whole journal club.
Well, yeah, I mean, I guess I propose that we become the Ozeki Journal Club so that we are free to discuss other things when they come up. And obviously you think
it's a good idea? Yeah, absolutely.
Ozeki Journal Club, and it's snappier. The OJ Club.
Yes, orange juice.
Yeah, exactly. So was that all we had to discuss? I think so. Yeah. I am going to share my screen so that we can see what's going on. This time I did some highlighting of the paper.
Beautiful. So
we don't miss any key points. Okay, so are you ready to go?
I'm ready.
Cool. So the paper is, I believe, a recent NeurIPS submission, and I think it was accepted. So NeurIPS is one of the largest machine learning conferences in the world, and it's recently like grown exponentially, obviously, as machine learning becomes more and more studied. So this one's called Erdos Goes Neural, an unsupervised learning framework for combinatorial optimization on graphs. And I thought it'd be cool because we kind of talked about combinatorial optimization with the Clique paper. I guess, did we call it Clique? Our paper on scaling, on using the Bitcoin mining algorithms for solving essentially combinatorial optimization problems.
What did we call that though?
What?
We call that something specific.
DIPS.
DIPS, that's right.
Difficulty based incentive problem solving. Yeah, difficulty based incentive. Yeah, so basically, I guess you can watch the video for that, but it was based on shifting the difficulty for solving a block in proof of work based on whether or not you've solved a certain combinatorial optimization problem or a certain NP complete problem. So this paper's from two authors. Perry, care to give me the pronunciation here?
Nikolaos Karalias and Andreas Lukas.
Very good. I guess those are pretty easy Greek names as far as I've seen.
I hope I didn't mess up the pronunciation though.
Well, you are a resident Greek expert.
Yeah.
So we have they're from EPFL, so they're from Lausanne, and yeah. So I've this kind of thing like combinatorial optimization and graphs and machine learning are things that I look at a lot in my research. So I thought this was a cool paper to look at. I'll give the broad overview and then we'll go through the details as usual. The title is Erdos Goes Neural because it's kind of giving a shout out to this really famous mathematician called Paul Erdos. And he was, do you know him, Barry?
I do not. No, I don't know.
He basically was like this wandering scholar. I don't think he had a house. He would just go to universities and write papers with people. And now in CS, like people talk about their Erdos number, which is how many hops or how many co-authored papers you are away on the shortest path to co-authoring with Paul Erdos. So Erdos has a number of 0, and then anybody he wrote a paper with has a number of 1, and so on. And it's like kind of a graph representation of, it's sort of like a network problem, and he worked, not problem, but a network-based way of being cheeky about Paul Erdos. So I think he would have appreciated it. I don't think he's alive anymore though. Okay, so that's a little background. So I guess I should say everything goes around this equation here, right here. So we're basically given a graph, which you can think of as 3 things. So a set of vertices, a set of edges, and a set of weights. And basically, a set of vertices, you can just think of it as integers, and E, you can think of it as pairs on that set. So, connections that form on the set V. And W is just some weight that you can assign to either the nodes or the edges of the graph. I'll show what a graph looks like down here. Here's a graph, right? Vertices and edges connecting them. And we can define many real world situations as graphs, social networks, citation networks, molecules, tons of things can get encoded as graphs. And then we can basically define some problems on these graphs, which we want to solve, and they usually give us some insights about the underlying data. So they give a sort of general framing for solving these kinds of problems on graphs. So basically, they're looking at a minimization, which operates over a function, which takes as input a set and a graph. And this set is usually a set of nodes, so some selection of the nodes in the graph, so some subset of the nodes. And basically, we can come up with different functions that accept those 2 things and tell you basically the quality of your solution, how good it is. So for example, I'll go back to this. One of the problems that the authors address is the maximum clique problem. And basically, given a graph, you need to find a set of nodes, which is a clique. And a clique is basically a set of nodes where all pairs of nodes are connected to each other. So they all have an edge between them, and is maximal. So it's as big as possible, includes as many nodes as possible. So for example, you can imagine any 2 nodes forms a clique because all nodes in the set have an edge between them. Obviously, that's a very small clique. You want to find the largest one that you can. And here they give an example of, they highlight in green all the nodes that form the largest clique possible on this graph. And they think we say this is a combinatorial optimization problem because finding the solution in a sort of a naive way involves enumerating a combinatorial or many combinations over a set of objects, right? And combinations often scale exponentially in how many nodes you're dealing with, and so they're usually very difficult problems. How's it going up till now, Perry?
Yeah, sounds good. Yeah.
Cool. All right. So
you're just defining what combinatorial optimization is basically.
Mm-hmm, exactly.
The equation 1 defines that completely.
Yes, except there is a constraint, which is the last thing to look at, which is I already alluded to, which is the selection of nodes which you think of as your solution have to belong to some set of acceptable solutions. So in the example of a clique, well, your solution set has to be in the set of all possible cliques, right? So it basically needs to follow the property that all nodes in this set have an edge between them. Right? Okay, so this is the problem they're trying to tackle, and people have been working on these problems for a very long time. And recently, there's been some advances in using machine learning to solve problems that previously didn't really have good solutions. And specifically, graph neural networks have become sort of the default machine learning architecture to use for graphs. And they're trying to see if they can use this framing for a combinatorial optimization problem to see if they can gain some benefit. And specifically, what machine learning has been useful for is in getting efficient solutions or good solutions for some like subset of all possible problem instances. So, and that subset typically is the one for which we have real world data for. So we can train algorithms to be really good at modeling the real world instances of problems. Whereas you can think of, like, in a theoretical sense, maybe like the problem of finding the maximum clique is really difficult for some really weird graphs that never really occur in real life. Maybe we can just discard those and train a model to learn how to do well on realistic graphs, for example. And I guess, yeah, so the graph neural networks have been really useful for that. Okay. There's been other like machine learning style sort of attempts at this, mainly using reinforcement learning. And that usually involves like kind of a different family of algorithms, and they suffer from sort of their own limitations, which tend to do with like making it very difficult to train these models. So they're trying to take a different approach, which they call unsupervised learning. Okay, so their whole thing basically has 3 major steps. One is you construct a graph neural network, we call it G theta, which outputs a distribution over sets. So it basically gives you the probability that a certain set has some desirable property. In the simplest case, we can think of it as a probability distribution over the nodes of a graph. And okay, so we basically instantiate this neural network, and we train it in such a way that there's a high probability that a good solution to f will be sampled. And then once this distribution is defined over the nodes of the graph, they propose a mechanism for actually going from these probabilities to an actual like solution, which is a set of nodes in the graph. Yeah.
So just to be clear, this G theta is a function, basically.
Yes, it's a function.
You input the set of all graphs, G, and then what's output is a probability distribution over the subsets of the graphs, I guess. Yeah, over the subsets of the graph that tell you how likely it is that that subset solves equation 1. Yeah,
exactly.
Okay, perfect.
I think so. I can give like a little picture of a graph neural net, actually. Let's see. Let me look up my supervisor real quick. I think this paper.
I think you're not sharing it right now, I guess.
I'm not sharing it? You don't see?
I think you're just sharing the page that you haven't shared your whole desktop, that's why.
Okay, how about now?
Yeah, now we see it.
Okay, so graph neural network is very simple. Usually looks something like this. Let me zoom in. So usually you have like, here's a graph, right? And usually each graph is associated with some data. Each node in the graph is associated with some data, which is just a vector. And the graph neural networks basically compute a vector for a given node based on some function which aggregates the vectors coming in from its neighbors. And you can do this in a way that can be optimized. So the neighborhoods get transformed with some weight matrix, some transformation matrix that you can sort of optimize with gradient descent. And so you can compute these vectors for nodes such that they minimize some such that they make it so that you can predict some property of the node, or such that you can reconstruct that neighborhood, whatever sort of criteria you want to give, the model can learn it. And because it operates on sort of the neighbors of the node and the neighbors of its neighbors, it's kind of intrinsically capturing the structure of the graph. And basically for this paper that we're talking about, the vector that's being computed is going to be just a probability value, right? Okay, that's just what a graph neural network is. But you're right; it's really just a function that accepts a graph and outputs some vector, right? Right. Where did the paper go? Okay.
So now we can't see the paper, unfortunately.
Ah, yes, of course. You share. Very good. Okay. Yep. So back to the paper. So they have this function g theta and has parameters theta, like we said. And so now they need a way to actually, train this function such that it gives us a solution to the combinatorial problem. And in the simplest case, like I said, they say that each node has a variable xi, which is a Bernoulli random variable with some probability pi, and that the probability is what the network outputs, right? So yeah, the network can trivially parameterize the distribution by computing the probability value for each node.
So it's converted this probability distribution over the subsets to a probability distribution over each node, basically.
Yeah, I guess they just wrote a very generic, a more general form.
Yeah. Okay.
But I don't think they use anything other than that for this paper.
Okay.
Okay. So in order to train this g theta, you need some criteria, some way to tell the model whether it's doing a good job or a bad job, so that you can update the way it aggregates vectors and computes this distribution to maximize performance. And usually that criteria, which is also called the loss function, should be differentiable, so that you can train this with gradient descent. And obviously, this f function is usually not differentiable. So it's usually a function operating over sets of nodes. And obviously that's not continuous. You can't differentiate over that. So they're trying to come up with a kind of surrogate function, which they can optimize, and that'll indirectly optimize this non-differentiable loss function or non-differentiable criteria f, right? And I think this is a key equation. So they're trying to come up with a model, a distribution D, which maximizes performance here, right? According to this loss function. So they want a loss function that upper bounds the optimization criteria f, right? Such that you have a probability larger than t that the value of your optimization criteria is less than whatever loss you're minimizing. I think that was confusing. That was a mouthful. 1 second.
Yeah, a bit confusing, but yeah, I guess you just put a bound on what you say the probability that your function is less than some loss is bigger than t.
Yeah, exactly. And so you're trying to minimize this function, right? Which is something I should have said.
Yeah.
So obviously, the smaller your loss is, the higher the probability is that you have a good solution. Mm-hmm. So you want this property to hold. And so basically they say, assuming that this function f is non-negative, they can use Markov's inequality. And that lets them write the loss function as basically this expected value over the original scoring function f.
And this expected value is with respect to the probability distribution d, script d.
Yes, I think so.
Mm-hmm.
So which we get from g theta, right?
Right.
So I guess you can get that explicitly, I would assume. What I was not too clear on is how they go actually from like Markov's inequality to this form here.
I think Markov's inequality just tells you this.
I don't know, because I looked up Markov's inequality, And if we look at my note here, actually, no, we can just look at Wikipedia. Go back to my browser. So it tells you that it's here, right? So probability that some random variable x is greater than or equal to some constant a is less than or equal to the expected value of x over a.
Okay, and you're saying we can't translate that over to
well, let me show
what they've written.
Yeah, it didn't seem to me like it followed directly, but I may be wrong here. I mean, I'm definitely wrong. Yeah, so here you have like a double inequality happening, right? Unless you treat this as x, like the random variable.
No, I think, well, maybe, but I just thought like L was x, F is a, or something, right?
No, T is a.
T is a, you're saying?
Yeah.
Isn't X bigger than A? Oh, man, I'm sorry, yeah.
Wait, I need to get back to it. Let me share. There. There's probability that X is bigger than some value A.
Yeah, so A is an AF. L is the X is the loss. X is the loss, and then.
I mean, they're just writing the loss as this, right?
Yeah, but I thought if you wrote. I just thought you can isolate this somehow. I thought it was just algebra after that. Like I thought you had to write Markov's inequality with respect to equation 2, and then using algebra you could get L.
Yeah, it could be, but like the equation for L really is the same form as this, right? Okay, yeah. So maybe like this x greater than or equal to a is directly this chunk, right? The f less than that.
That's what I thought, but it actually looks like x should be f. Okay, yeah. So this is the inverse Markov. It's the opposite of Markov's inequality, right?
Yeah.
Instead of less than, it's bigger than.
Mm-hmm.
So f of s, g is x, L is a, and yeah.
Okay.
And then if you have Markov's inequality with respect to that, I think you get the next equation.
Okay.
We should have maybe done this before, but
no, it's fine. I mean, I believe that it follows.
Yeah.
Okay. So yeah. Okay. So what that means is now that you can work with this expectation, right? And that'll sort of indirectly be an upper bound on f. So the lower you get this function, the lower you sort of squeeze the solution score, right?
Yeah, and I guess the point is this expectation is differentiable.
Yes. Which they don't say explicitly that they're using this d over the expectation, but I mean, I don't know. They say if the expectation can be computed in closed form, any upper bound also suffices. But yeah,
if it cannot, yeah, okay.
If you cannot.
Yeah, so you can just pick any upper bound of L basically, and then you can use that.
Yeah.
And then make that smaller, and then you're fine.
Yes. Yes. So they say, yeah. So essentially, they say it's like a certificate, right? Lowering this L is a certificate for having a high probability of finding a good solution. Okay. Boop, boop, boop. Okay, so that was kind of one piece of the puzzle, but another big one is that they haven't dealt with like this constraint sort of component, which is, well, you can't just pick any set of nodes. That set of nodes has to have some property, and we call that property omega. So they add a term which is a penalty, right? So you can't just maximize the score, which would just be, for example, in if you're doing maximum clique, maybe this f is just counting the size of the clique, right, or the size of s. And that would obviously give solutions that aren't always cliques. So you add this term here, beta, indicator times beta, which says if S is not a valid solution, then this becomes 1, and then you incur a penalty of beta. And I think they say that as long as beta is larger than the largest possible solution, then the model will never pick an invalid solution, right? Because yeah, F will never outweigh an invalid beta.
Right, yeah.
Cool. So yeah, this becomes what they want to do now. Now they have this extra constraint on the same equation that they had before. And I think, yeah, they also want this to be differentiable. So the way they estimate this probability that the solution is not valid, they also want that to be differentiable, right? That way you can directly optimize everything with gradient descent. This the linear box constraints. Yeah, so they talk about a special case, right, where you're trying to minimize the function with like some the solution being in some range. But I looked at supplemental and they never defined AI again. So this part I kind of like skipped through a bit. But basically, okay. I think they're just trying to like, I think they're trying to come up with like these like rescaling coefficients. So they're trying to scale their distribution, which are the PIs that they try to compute, with some coefficients AIs, such that the solution falls within some interval. And they come up with some like iterative approach, like you try a set of coefficients, and then if that doesn't work, you sort of gradually adjust them until they fall in the range.
But your solution isn't it? Aren't you trying to find the minimum?
It's the minimum subject to this constraint, right? That
I see. So okay. So adding another constraint. Okay.
Yeah.
Okay.
So I think maybe this is like an easier. I guess I think they gave it as an example of like having differentiable constraints, right? Okay, and then so if you're able to have a formulation that's fully differentiable, and that has this upper bounding property on the actual function you're trying to optimize, then the last thing you need to do is to retrieve a full solution, right? Because you start off with just probabilities on nodes. Now you want to return someone an actual clique. Mm-hmm. I think they say that you can do something very simple, which is sort the nodes in decreasing probability. So once your model is trained enough, you just basically start with the node that has the highest probability included in your solution set. And then you look at the one with the next highest probability. And if including that node increases your score, then you keep it. If not, you throw it out. And later on, they give a version with constraints. Like I think they just say, okay, if your node doesn't follow the constraints, you throw it out. Right. I don't think they gave a proof of like this being a legit way of doing things, but I think it seems like it's a.
Because what happens if the first node doesn't satisfy, like doesn't maximize the probability eventually? Yeah.
They say it's like a standard thing to do though. Reference 54. Sure. It's often used in combinatorics to de-randomize probabilistic proofs and obtain deterministic algorithms. Yeah, but I don't think they gave a proof in the supplemental of this, so I think it has to be trusted. So yeah, I guess I don't know. There's some property that they're probably taking advantage of. But then they say, okay, well, we can do this. We can define everything in an unsupervised way, which means that they only need the graphs themselves to be able to train this model. Previously, like other methods were saying like, okay, give us a set of cliques and our model is going to learn to replicate those cliques, for example. And somebody would have to go and manually say like, okay, these are the cliques, you know? But here they're saying, okay, we're going to work directly unsupervised, directly on the graphs. And they apply it to the clique solving problem, maximum clique problem. So they just restate the actual clique problem here in the same form as equation 1. So they say, yeah, you're trying to minimize the negative weight of your solution set S, and W is, in the simplest case, just the number of nodes, but they have some generalization which lets you like put weights on each node. So minimize the negative is the same as maximizing the clique, and obviously the solution S has to be in the set of all possible cliques. Okay. Yeah, so this is their loss function that they derive. And it comes from computing the expectation of this f of s, which is like that they define here, the sum of the weights of the edges.
Yeah, so I guess it is using this D, right? Because these PIs are the Bernoulli probabilities.
Yeah, exactly.
Yeah.
So,
okay, so
they do it in supplemental. Actually, we can look at it.
So it comes from this D probability distribution.
It does, yeah. Here, yeah. So they're basically computing, yeah. So the WS is the sum of the weights of the set, sure. And then they just compute the expectation of that, which is just like the weight times the probabilities that the model assigns. And so that's their expectation value, right?
Well, yeah, so X is the random variable, and the expectation value of X, if it's Bernoulli distributed, is this PI.
Mm-hmm. Yeah. And okay, so that's kind of like the objective function you're trying to maximize, and then they include the constraint penalty here, which is the probability that the set is not a clique. And yeah, so here I found like I didn't get this equation, but they're trying to basically come up with. Yeah, but I mean, okay, so I'll look at it. It's basically, I wrote down, it's a sum over pairs of nodes in S that don't share an edge. So they define this complement of S, the weight of the complement of S is basically the sum over all pairs of nodes in your solution set. And then you do something to the ones that are not connected, that don't have an edge, right? I don't know what this sum means. Like, do you add one every time they're not connected or something?
Oh, I thought so, yeah.
Yeah, it could be a count, but maybe like it can also have some weight added to it. But then they say like if basically saying the probability that a subset of nodes is not a clique is the probability that this sum is greater than or equal to 1.
Okay, maybe it's scale you're saying.
Yeah, so I mean, I would imagine it greater than or equal to 0, right? Like as soon as you have a pair of nodes that are not edges, that are not connected by an edge, your probability
should drop to 0.
Yeah, but I mean, I think I'm misunderstanding this notation here.
Yeah, I mean, it could be scaled or shifted or something. Yeah, I don't know either.
Like this is not a sum over anything, right? Like what is this?
Well, a sum over nothing. I guess a sum is just you add ones, but usually, right?
Oh, sorry. This is a set, right? This is the set of Vij pairs that don't belong in the edge set.
Sure, but is that the norm of the set? The order of the set?
Yeah, I don't know. Right? Like, but it's a set that involves only one.
It could just be brackets, right? It could just be bracketing the term.
It could, I guess, but still doesn't mean anything, right? Like it's not adding anything.
Yeah, so it looks like it's saying sum over. Yeah, I'm not sure either. I don't know what the notation means either. Maybe curly brackets is a specific notation for something.
It could be. I mean, they define this W of S before as oh wait, even here they define it. Yeah, it's basically the weight over the edge, the sum of the weights of the edges, right?
But there's something to sum over.
Yeah, here there's something to sum over, exactly. Here there isn't. I don't know. I'm confused by that, but I think at the end of the day they're just trying to get this probability, right? That a set of nodes is going to belong to a clique.
Yeah. I'm trying to look it up, but I don't think there's anything specific about.
What do you think you would look up here? Oh,
like
right.
If curly brackets mean something specific, like it's some sort of notation, maybe. Yeah, I don't think so. Anyways, I think we get the gist, all right? You just want to create. So. You just want to have something that can be that you can use as a penalty.
Well, they define before that they say that they define W bar S to be the volume of S on the complement graph. The volume of S, they said earlier, is the sum of the degrees of the nodes in the set. But I don't know if that applies here implicitly somehow.
Yeah, I'm not sure. I think it's fine, to be honest. I think we understand what they're trying to do, at least.
Yeah.
The math is not maybe 100%, but we understand, I think, that...
Yeah, so that's where this second term comes out, though. So this first term is that expectation that was derived before, and then the second term is the constraint.
Okay, yeah, and that's why they say gamma is like some huge positive number to keep everything positive, I guess.
Yeah. They end up scaling everything here. Gamma is an upper bound, so that everything is positive. Exactly. Okay. All right. And yeah, so once they have that, basically they're good to go. You can now everything is differentiable. So you can just plug this into a gradient descent solver, and these probabilities end up approaching, giving you a good solution, right? And then they do this decoding step, right? Where basically, what do they do? Yeah, they sweep the nodes in order of largest to smallest probability, and they add them as long as you still have a clique, right? And since it's very quick to check whether or not a node is breaking the clique constraint, then you can do this just by a one sweep over the nodes. I still am not super convinced about this. Like, I don't know. It feels a bit counterintuitive that you can just go over nodes in that linear way.
Yeah, at least you should do this thing. I thought, like, where you don't eliminate the possible, like,
yeah, you do some branching.
Yeah, you do some branching, exactly.
Yeah,
I'm not sure. They give a reference. I guess you'd have to read the reference.
I guess, like, if you think about a clique, right? This example here. Oh my god, this, right? Like, you have to assume that all the nodes here have a higher probability than all the nodes here, right?
I guess the central node would have the highest probability.
Why would it have the highest probability?
Isn't it?
Because it has the highest degree.
Yeah. It's gonna get to everything, yeah.
Yeah. Well, no, they all have the same degree, right?
Do they?
In a clique.
Oh no, but I mean, but sure, but I guess
the whole graph.
Yeah, over the whole graph.
Yeah. But the thing is, like, that you shouldn't, like, you can't encounter a node that doesn't belong to the clique if you're going in this, like, sweeping manner, right?
You can't, really?
Like, all the red nodes should have a higher probability than all the black nodes.
I guess.
Because, like, if you pick this one as the highest probability, then maybe this one has a higher next highest probability. It's still in a clique, right? So you take it, and then you're stuck with, like, a clique of size 2, right?
That's what I'm saying. Like, why can't that happen?
Yeah, I know. I don't know why that can't happen.
Like, what if that black node you just pointed to is very connected to other nodes, but it's just not a clique,
But it would still form a clique with the previous node, which had the highest probability, right?
Sure, but then you have a clique of size 2, and the problem would be broken.
Yeah. Well, I guess, like, the probabilities are also tuned by the constraint, right? So if the probabilities would lead to non-cliques.
Yeah, so you're hoping the black node eventually has lower and lower probability as you run the graphical network.
But then I would imagine that you don't need to decode, right?
You just pick the ones with the highest probability.
Yeah.
I guess the decoding was a check that they make a clique up,
Well, according to them, yeah, I find it weird because in the results they claim that they always get. I mean, the way the constraint is formulated, the model would never produce invalid cliques, right? Because it's always cheaper to have a smaller solution than it is to create an invalid one.
Yeah, but you're not outputting cliques, right? You're outputting a probability distribution over nodes.
Yeah, yeah.
So then from there you have to construct the clique.
Mm-hmm.
And I guess it's like, how do you construct it? Like you let's say you pick 2 nodes, then 3, then 4. Eventually your clique is done, right?
Mm-hmm.
And picking a different one would drop the probability back down to 0.
Yeah.
So I guess that's what you're trying to do, or that's what you're trying to write down mathematically.
Mm-hmm. Yeah. Very crazy. Okay, let's go back up. Boom, boom, boom. All right. So yeah, I think that's straightforward. So the loss function basically has the same 2 terms, right? The objectives you're trying to maximize or minimize, and then this penalty. And it's up to you to basically derive these, right? But I think the point of the paper is to come up with a general framework. I guess then they just give another example. I mean, I don't know if we need to go into it, but they were also able to solve the problem of graph cutting, which is saying if you have weights on your nodes, try to find 2 subsets of the graph's nodes that together contain all the nodes, and that the edges connecting the 2 sets have the smallest possible weight. Did I say that correctly? So find a set such that the cut S. Yeah, so you're summing the weight over the nodes, over the edges that go from the solution set to the outside.
I see. You want to cut the ones with the most weight.
You want to make the cut that has the smallest weight on the edges, right? Like maybe I can show an example.
Yeah. Maybe I said the wrong thing though.
It's the min cut problem. What's a good one? Here, I guess. Is that a good one?
Well, it depends on the weights, right?
It depends on the weights. But if everything has a weight of 1,
yep.
Then yeah, so you're summing over the red edges basically. If this is your cut, you sum over the red edges, right? And you want the sum over the red edges to be as small as possible.
Okay. Yeah. Yes. So you want to maximize the other cuts, the other sum. Mm-hmm. Sorry, the sum over the black edges.
Mm-hmm. Yes. Yes.
It's the same. Yeah, it's just 1 minus.
Yeah. Okay, cool. So back to this. Yeah, so they had a similar formulation. So basically they have to come up with an expectation for this cut property, and they have to constrain the solution to this interval. So I think that's where like that interval constraint thing comes in.
But what does it mean to constrain to some interval?
That the solution has to be within VL and VH.
Okay, so they don't want to minimize. They just want to find some solution between those 2 values.
Yeah, I guess that's like an easier case.
Okay.
Let me see quickly if by scanning through solutions in different volume intervals and selecting the one whose cut over volume ratio is the smallest. Yeah. Yeah. And then again, they have the same. Yep.
The expectation value again.
Yeah.
And then they get this this long equation here.
Yeah. Which I didn't look into a lot. But what's the constraint? Oh, yeah. I mean,
the constraint is the volume. S is in the interval, right?
Why would that have to be a constraint?
I think that's the point. I think what they're saying is that they do this for many different intervals, and then they just pick the smallest interval.
No, I know, but I mean, there's no like omega here, right? Like the property of the solution that they need to maintain. I mean, I guess it's that its volume is within this interval.
Yeah.
But I mean, yeah, I mean, I guess I don't know why. Like they could have just solved directly the cut thing, right? Without any volume function on top of it.
Well, if you scroll down, there's no beta here, right?
No. Yeah, I mean, I just feel like this volume thing was an added constraint, right? It didn't have to be there. Like you would still get something interesting from.
I think that's
like,
I think that's what they're doing though. There's no constraint beta thing here, I think.
Yeah.
Unless D is the beta. I'm not sure. No,
Harder
D.
variants of partitioning aim to provide control on partition balance as well as cut weight. Okay, so maybe like it's more interesting to have it within some volume than to just like, yeah, I mean, this problem is you can solve it like with like in polynomial time.
Okay.
You don't need machine learning or anything for that.
I see. Okay, so maybe it's non-polynomial if you have a constraint.
Yeah, I think so. I just realized that. Whoa, everyone's seeing my emails. Okay.
They can now pause and like.
I'm not editing this now. Also, what's nice is because we're only two people, we don't have to restart the Zoom.
I see.
Yeah, isn't that lovely? Okay, so basically they gave an example that works. They gave formulations that work for two combinatorial optimization problems, which was like, for me, a bit of a letdown from the title.
You're expecting a more general thing?
I was expecting a somewhat more general thing.
Okay.
But I mean, I think it's still pretty cool.
But I guess the formulation is there to generalize, right? I guess the novelty is coming up with this loss function. That's the expectation value, which is and the Bernoulli part, which makes it so that the loss function is differentiable. Yeah,
for sure. But I guess it still requires like, I mean, I don't know if it works for all graph problems, you know? I guess for the ones that you can compute this expectation, right?
Yeah, but I think you can for everything because it's just Bernoulli, right? You know the distribution.
You know the distribution, but you don't. You need to optimize this expected value.
But you can calculate that analytically because you know the distribution is Bernoulli. No.
Yes, but I mean, it still depends on the problem itself, right?
Yeah. So there's a graph. There's a graph neural network part also. Like
no, I mean, like the way they got this W here. Right?
Yeah.
This W needs to translate to like a differentiable expectation, right?
Okay, you're saying like, what if your function that you're trying to minimize is not continuous or something?
Yeah, something like that. Like, I don't know if there are some graph problems where you can't just write down this expectation, right? Like, I don't know if they can claim that this works for all combinatorial optimization problems.
Okay, maybe there's a constraint on the functions you have to consider.
Yeah, like for the Clique, okay, it's straightforward. You're trying to like maximize like the connected graphs, the weights of the connected nodes, right?
Yeah.
But I mean, I'm sure there's like other graph problems where it's like not as, straightforward.
Sure.
So that in that sense, I don't know how general it is, but I guess, yeah, if you can get that formulation, then the rest follows nicely. And yeah,
so here you've highlighted almost the whole thing.
I highlighted almost the whole thing because I was kind of like not super clear what was like the main takeaway from their empirical tests. It sounded almost like they kind of went back and forth on like how they compared with other tools.
But they gave a limit in which they think they're better, right?
Yeah. So like, I mean, overall, they compared basically to other neural net approaches, and also to like to discrete algorithms. So like exact algorithms you can write down, and to like just constraint solvers. And they do this like on a time budget, which I think was nice. Like if you give both models the same amount of time to work, which one gives the best solution? And I think at the end of the day, they make sure that like they're not like showing that their model is better than every other model. I think they just wanted to show that this is an interesting way to phrase the problem, and it needs some improving. But like it seemed like they were able to work well on larger graphs, I think maybe their main takeaway. Yeah, so I think the best tool was this Gurobi, which is just a solver, but it didn't work well on large graphs, and it seems like theirs was able to do better on large graphs, So it says both neural approaches fall behind the greedy algorithm and Gurobi, especially when optimizing for quality. The performance gap is pronounced for small instances, but drops significantly for larger graphs due to Gurobi's high computational complexity. Okay, so it seems they're able to work nicely on larger graphs.
Yeah.
But the performance degrades when testing in larger problem instances. Like I just found like it's going in circles a bit.
Sure.
Like they say they do well on large graphs, but then they don't do well when the graphs get larger.
Oh, is that what I was saying? Maybe.
Yeah, look. The main weakness of Erdos GNN, which is their tool, is that performance degrades when testing it in larger problem instances. And then they say,
however, in the training set, test set, and worse for larger.
Even larger, right? We hypothesize that this phenomenon will be more pronounced with larger graphs. Like, I'm not sure if they're saying they do better on larger graphs. Okay, I mean, we have a table, right?
We're actually just okay at everything.
I mean, yeah, it kind of seems like it. Okay, look, large instances, 0.7, 0.7, and then they have Gurobi doing 0.8, 0.79. So like, it looks like on large graphs, Gurobi's doing better, right?
We even have a 0.83 here on the Tonschoff greedy.
0.83.
0.89 there. 829.
On which column? Large instances? Oh yeah, here, sure. Yeah, so I think that's just an exact algorithm.
Oh, I see.
So, I mean, I actually don't know what these different rows mean. I guess they're different time budgets.
Yeah, I guess 0.1 second, 0.5 seconds.
Yeah. Yeah, so I mean, Gurobi's always beating it, right? Even on larger graphs.
But just not for little, like if you lower the time.
Yeah, I guess on a low time budget, they can do really well, I guess.
Well, comparatively, I guess. Yeah.
Yeah, comparatively. This one was on real world data sets. Okay.
Here they're beasts, right?
Here they are beast.
Twitter at least.
Gurobi just destroys everything, right?
No, but look at the Twitter. In the Twitter column.
Twitter column, yeah. Okay, yeah.
CBC gets 10%.
Yeah, sure. I should say that this percentage is how close you are to the optimal solution.
I see.
So it means that after, I think, 0.17 seconds per graph, they were able to get 94% within the optimal, 92% within the optimal. I don't know. I found these tables kind of hard to read, though, to be honest.
Yeah, I think they're just saying that maybe they're saying they're comparative to other results that are either exact. Like, I don't know. Maybe there's ways you can improve machine learning, but you can't improve these exact algorithms.
I mean, maybe you can, right? Like, you can just come up with a better idea.
I guess, yeah.
That's what like a lot of people in my group are like kind of upset about with machine learning. Like
people tune parameters to get better numbers instead of coming up with smarter things.
Yeah. Okay. Exactly. Which, I mean, I guess I kind of agree on, but what's nice about the machine learning thing is that like if you do it enough, then you can do well at everything, you know, automatically. Like the idea is you can have just like one big machine that can compute anything.
Sure. Okay.
And you're never gonna come up with enough clever ideas to do that. Mm-hmm. Like clever tricks, you know? Like, okay, nice, you found a clique for the maximum clique problem. Now like do something completely different.
You need a trick.
So it's like, yeah, okay, machine learning is like annoying because it does well and it doesn't really require like thinking about the problem, you know? Mm-hmm. Like these guys never thought about what it means to have a clique in a graph, you know?
Sure.
So I guess that's like, I don't know, that's kind of like a point of contention. But I mean, they still have to come up with like a smart sort of framing of the problem.
Right. No, it's true.
So yeah, okay, I mean, I can understand like if people are like algorithmic people, you know, they spend a lot of time thinking up like very precise algorithms. Mm-hmm. And then one guy's like, look, I'm just going to burn through a bunch of GPUs. I wrote down 3 equations and
my supercomputer is bigger than yours and I don't care.
Yeah, I mean, it's also a concern. Like, I'm surprised they didn't mention it in their broader impact statement.
Yeah.
That like I don't know, people I talk to are like, oh my god, I had a bug in my code. I need to redo the training on the GPUs, you know. And it's
Oh,
like,
okay.
bro, we just burned so many trees, you know, because for nothing, because obviously, you know, these GPUs are taking up a lot of energy.
No, sure. They could be mining Bitcoin or something, you know?
Yeah.
No, no. Well, yeah, GPUs can, I guess. Not Bitcoin maybe, but
I wonder if no, I mean, you can't use these GPUs for anything useful. You got the problem of dips. Yeah, but obviously we have to mention that they had to write this broader impact paragraph.
yeah, which I've never seen before in my life.
No.
I think we checked. It's like NeurIPS forces you to do this, right?
Yeah, this year now you have to do it. And it's just, I feel bad for them, you know? They had to think about how finding cliques is gonna like destroy humanity.
Yeah, yeah.
Worker displacement. I think you had an argument for the worker displacement thing, no?
What do you mean?
Like it's not a problem that machines are replacing people because
Well,
they'll
it might be a
always
problem.
generate.
So in the short term, it might be a problem, right?
Yeah.
But I think we want society to get more efficient.
Yeah.
Like we want to move people to like if you're more efficient, then it costs you less to do things, and then you can train these people that are being whose job is being destroyed to do something more useful for society.
Yeah.
I don't know. I guess I just don't like the argument of saying let's keep everything stagnant so people can keep their jobs.
Of course.
I mean, of course, I want people to keep their jobs, but I mean, you can get maybe we can give them better jobs. You know, jobs that are better are more useful for society in general.
Yeah, I agree. But maybe it has this assumption that like there will always be problems to solve for people, you know? Like you can imagine that at a certain point, like we've automated everything and people are now
Maybe
useless, you know?
sure, but maybe now we work. In that case, maybe we work 4 days a week instead of 5, and you know, there's more benefits for everybody. And I don't know.
Yeah, I'm down. I don't see this paper causing any societal problems, to be honest.
It's true. Maybe people don't have to count cliques anymore. They might lose their job, but I don't know. Maybe that's a good thing because those people can have more time to do other things or be trained to do other things.
Probably. So yeah, here's their like. I found it funny that this kind of went supplemental, you know.
Is there a length limit on the NeurIPS papers?
Yeah, I think there is. I think they're gonna do a 10-page. Is this 10 pages? Yeah, it's 10 pages. Oh no, it's 9. Oh my god, not even. Yeah, it's 9 pages. Okay. Well, including this broader impact thing, it's actually just 8. Wow, that's crazy short. I guess because they had 0 figures, so it's a lot of text. Yeah, this would have been a nice figure to put in there. But actually kind of boring. Like, yeah, so I guess they just showed like how you can go from these, I guess these colors should be shaded proportional to a probability.
Right.
And then at the end they become one set, you know? And that's your solution. I guess it's interesting to see like also how it behaves on like graphs that have like solutions that are like very close to each other. You know, like I don't know if like they can sort of, yeah, it would have been interesting to see that impact. But obviously, like that must happen, right? Because they trained on really huge graphs.
But these cliques, for example, are very like the clique on the right and the clique on the left.
Well, it's the same graph, no? Oh, like this and this?
Yeah, but they're very close to those cliques, right?
Yeah.
They still got the. Wait, what are you're saying? Like, I don't know what you're saying actually. What do you mean?
No, I'm just saying like it. Obviously, you can come up with like if you were to kill all these edges here, it would be a lot easier to find the distribution would be a lot more pronounced, you know?
Sure.
Like
yeah. Okay, so how sensitive are they to like these to a very slight increase in like so if there's a clique of size 1,000 and a clique of size 1,001, can they get that clique of size 1,001, say?
Yeah, exactly. Especially because you have like this really smooth sort of space, right?
Yeah. It probably depends on the input and everything, right? Like it's
yeah.
You might get stuck in a local minimum.
Yeah.
I mean, you probably will get stuck in a local minimum.
Yeah, that's the other thing. You have local minima. But I mean, it seems like, what were the numbers they were getting?
80% or something, 70%?
Yeah. I guess that leaves like a lot of space for possible suboptimals.
Right.
Interesting. Okay, well, I mean, yeah, this is, I think maybe we can recap it. So like they said, their contribution is just a mathematical framework for solving combinatorial optimization problems on graphs using graph neural networks. As long as you can write down the constraints of the problem in this differentiable setup like this.
Yes, I think equation 1 is more their main result, right? Or the equation after equation 1?
The Markov one, right? This.
Yeah, this equation 2 and the equation right after.
Yeah.
I guess this is the main result. If you assume D is a Bernoulli, these expectation values can be computed, at least for the two problems they present. And then everything is differentiable, and you can train your graph neural network with gradient descent, and everything behaves nicely.
Yeah. And one interesting thing that they mention is that their model doesn't do well on the test set, which I guess is what they wanted in a way. Like they want their model to just focus on the distribution of data, a data distribution that it observes. So I guess you can see the trade-off, right? Like they're not saying that they can solve this for every possible graph.
Right.
But once they've seen these graphs long enough, then it starts to recognize patterns. And I wonder actually if in these budgets, they're including training time, you know?
But I think they have the training time out on the previous table or the next table maybe. Or
like it's one thing like, okay, once you've trained the model.
The training, right? It's 0.27 seconds per graph. 0.5.
That's for training?
I thought, well, it says training. The first column says training set.
Oh, but on the training set, like that's just like, I guess there's a stage where you're like trying to compute the distribution, right? Or trying to get the function that gives you the distribution optimized. And then once you do that, then you just apply the model to a new graph, right?
But I thought that's what the training set would do, right?
Well, they have this decoding thing that like, I don't know if
I thought you train on the training set. Sorry, you train on the training set, then apply it to your test set after it's been trained. And then from there you can do the decoding.
No, I think the decoding is being done on both.
Oh, I see.
Like I think the training set refers only to
yeah. Well, sorry, go ahead.
Just like minimizing the losses of training set, right? And
the training set allows you to get these PIs.
Yeah.
And once you have the PIs, you can just apply it to the test set. At least that's what I thought. Maybe not though, because there's different timestamps, different time budgets for.
Yeah, but I guess the time budget can be consumed by the training time, like while you're doing gradient descent, right? It can be consumed by the application of the function, like input the graph, output the probabilities,
right?
And it could be consumed by like given the probabilities, decode the graph, right?
I see. Yeah.
And I wonder if like they're sort of recounting the first part, like the training part, on these different like setups, right?
Okay, this I'm not sure about.
I guess they must, like, yeah. So if the model is given more time, does it change these probabilities, or they're just like spending more time on decoding the graph? That's kind of what I'm wondering.
Oh, I see.
But I guess since the decoding is, yeah, I mean, they kind of mentioned that the decoding is time consuming, right? So I wonder if like the longer you decode, the better solution you get. Obviously, the longer you train, the better solution you get.
Yeah.
So yeah, I don't know. Anyway, okay, so yeah, that's the recap. I went back in the circle there, but I think we got the main point. Any other thoughts, Perry?
I think that's it. When is NeurIPS happening?
I think it happens in the summer.
Okay.
Ooh, there's my dog. Let's see. NeurIPS 2021. I wonder if they're going to do it in person.
Who knows?
July 27th. Oh, no, that's 2020. No,
next one,
2021. Right? Here. Oh, in Singapore.
Nice.
Yeah.
Are you gonna attend?
If it's online, yeah. What is this? Oh my god, that was a spam website.
Oh my god.
Freaking DuckDuckGo, it gives nothing relevant. Oh no, here. For real, it's very bad. Like I've spent a lot of time like, Googling a bug without solving it at all, and it's like, okay, fine, I'll use Google now. 20, what the hell? There's no 2021.
2021, November 27th to December 5th.
What? Oh, it is in the winter. Yeah, I went to the one in Montreal. It was here. It was snowing. Yeah. So many conferences.
It's coming up then.
It is coming up. Yeah. You can go, eh? Oh, let's see if the papers are there. Accepted papers. Let's see if our guys from this one are there. Why is my internet so slow? These conferences get such a crazy amount of submissions. Conference sessions, Monday, December 7th. Perry, let's go. Oh my god, it wasn't found. But why does it say 2020 though?
It's coming up.
Oh, because it is 2020 right now.
Yeah. Yes.
Oh my god. Yeah, you know what? I'm confused because I just submitted to Recomb, which is 2021.
I see.
This is our paper, Perry.
Nice.
Ooh, I shouldn't say that because it's anonymous reviews. Hope the reviewers don't see it. We're the first ones too. Submission one.
Beautiful.
Pricing. $100. Oh no, for students 25. Yeah. It's fun. It's fun, especially if it's online. Honestly, I just look at the list of papers and read the papers.
Yeah, makes sense.
I don't find the talks often that useful. Anyway, okay, so that was the paper. That was fun. Our first non-blockchain paper. Hopefully that went over okay. I have no idea what to do for the next one. Whoa, that was my thesis. Okay, I'm sharing too much stuff now. Speaking of my thesis, I'm not close to being done. It's really annoying. I'm not into like writing this introduction stuff.
Sure. I think everyone goes through that though.
Yeah. Okay. So let's call
nice
it.
Presentation. Yeah. And we'll figure something out for the next one.
You're picking the next one, eh?
Yep.
I'm excited.
Sounds
okay.
Good. See you later.
Ciao.
Thanks, Carlos.
Stop recording. Thank you.